In the previous lesson, we learned the core supernode idea. When a voltage source connects two non-reference nodes, we enclose both nodes and the source in one boundary, write Kirchhoff's current law for that boundary, and add one constraint equation from the voltage source. Now let us practice with two more examples. The first mixes an ordinary node with a supernode. The second uses two source branches tied to one top node. In both cases, the method stays the same. Identify the boundary, count only crossing currents, and use source polarity for the constraints. Here is example 2. On the left, node VA connects to a 6 kilo-ohm resistor to ground and a 14 milliamp source pointing upward into the node. That same node connects through a 12 kilo-ohm resistor to node VB. Then a 6-volt source connects VB to node V1 with the positive terminal on the VB side and the negative terminal on the V1 side. At V1, a 3 kilo-ohm resistor goes down to ground and a 2 milliamp source points downward from V1 to ground. The supernode is only around VB, the 6-volt source, and V1. Node VA stays outside, so we will write one ordinary KCL equation at VA, one supernode KCL equation, and one source constraint. Our goal is V1. Start with the ordinary node, VA. Its leaving current equation is VA over 6K plus VA minus VB over 12K minus 14 meter equals 0. Multiply by 12K and we get 3VA minus VB equals 168. Now write Kirchhoff's current law for the supernode. The crossing currents are VB minus VA over 12K, V1 over 3K, and the 2 milliamp source leaving the boundary. So the equation is VB minus VA over 12K plus V1 over 3K plus 2 meter equals 0. Multiply by 12K and we get negative VA plus VB plus 4V1 equals negative 24. The source constraint is simple. VB minus V1 equals 6. Now solve the three equations. From the constraint, VB equals V1 plus 6. Substitute that into the supernode equation and it becomes VA minus 5V1 equals 30. Put the same substitution into the first equation and we get 3VA minus V1 equals 174. From the first reduced equation, VA equals 5V1 plus 30. Substitute once more. 3 times 5V1 plus 30 minus V1 equals 174. So 14V1 equals 84 and V1 equals 6 volts. Then VB equals 12 volts and VA equals 60 volts. The check is clean. Negative 4M plus 2M plus 2M equals 0. Now example 3. There is one common top node, labeled V0, across the 4 kilo-ohm resistor on the right. 3 branches connect that top node to the bottom reference rail. The left branch has a 30-volt source on top and a 2 kilo-ohm resistor below it. The middle branch has a 20-volt source on top and a 5 kilo-ohm resistor below it. The right branch is just a 4 kilo-ohm resistor. Because the two voltage sources connect the top node to two internal nodes, the supernode now contains the top node, both sources, and the two internal nodes beneath the sources. The only currents that cross the boundary are the currents through the 2 kilo-ohm, 5 kilo-ohm, and 4 kilo-ohm resistors. Our goal is V0. First, write the source constraints. For the left branch, the top node is 30 volts above the internal node, so VA equals V0 minus 30. For the middle branch, VB equals V0 minus 20. Now apply Kirchhoff's current law to the whole supernode boundary. The current through the left resistor is VA over 2K. The current through the middle resistor is VB over 5K. The current through the right resistor is V0 over 4K. Their sum must be 0. After substitution, we get V0 minus 30 over 2k plus V0 minus 20 over 5k plus V0 over 4k equals 0. Multiply everything by 20k. That becomes 10 times V0 minus 30 plus 4 times V0 minus 20 plus 5 V0 equals 0. Expand the terms and we get 19 V0 minus 380 equals 0. So the answer is immediate. 19 V0 equals 380 and V0 equals 20 volts. Now compute the internal node voltages from the source constraints. VA equals 20 minus 30, which is negative 10 volts. VB equals 20 minus 20, which is 0 volts. The branch current check is elegant here. Through the 2 kilo ohm resistor, the current is negative 10 over 2K or negative 5 milliamps. Through the 5 kilo ohm resistor, the current is 0. Through the 4 kilo ohm resistor, the current is 20 over 4K or positive 5 milliamps. Negative 5M plus 0 plus positive 5M gives 0. Correct. These two examples show the range of the supernode method. Example 2 needed one ordinary KCL equation plus one boundary equation. Example 3 used source constraints first, then one boundary equation solved the circuit. So remember 3 rules. Count only currents that cross the boundary. Every ideal voltage source inside the boundary adds one constraint. And any ordinary node outside the boundary still needs its own Kirchhoff's current law equation. In the next lesson, we will move to supernodes with dependent sources.